So good morning, everyone. My name is Adan Patwaran, and I'm the project leader for EM Resources and the EMDB at the Protein Data Bank in Europe. Today I'm going to give a webinar on exploring EMDB. And you all are probably familiar with the EMDB as the archive for depositing EM 3D EM reconstructions generated by single particle EM as well as electron tomography. What I'll present today are web-based tools developed by the Protein Data Bank in Europe for searching, analyzing, and visualizing EMDB data. So Protein Data Bank in Europe, or PDBe for short, is a part of the European Bioinformatics Institute. Which is the European Bioinformatics Institute is the EBI for short, which in turn is a part of the European Molecular Biology Laboratory, or EMBL for short. So EBI is a leading center for bioinformatics with archives and resources stretching everything from genomes all the way to systems biology. PDBe is responsible for archives and resources related to molecular and cellular structure, notably the EMDB as well as the Protein Data Bank PDBe archives. So the EMDB, or Electron Microscopy Data Bank, was founded at EBI in 2002 by Kim Hendrik, and since 2007 it's been operated jointly by PDBe and RCSP under the aegis of the EM Data Bank project, which was funded by NIH and jointly awarded to Baylor, PDBe, and RCSP since 2007. We also have additional funding from EMBL, EBI, BBSRC, and the EU. And this graph here shows you how the number of maps released have progressed over time. And as you can see, we have had a healthy growth, and today we have more than 1,800 released maps, of which the majority are single particle EM maps, although subtomogram averages form a growing proportion of released maps. I just want to introduce a few useful websites for information about the EMDB. So the EM Data Bank project website is emdatabank.org. And this has both useful information on EM as well as links to partner site resources. The Protein Data Bank website, pdbe.org, is rich with resources both relating to EMDB as well as to PDB. And in particular, if you go to pdbe.org/EMDB, you reach the PDBe EM resources page directly. And the demonstrations that I'll go through today can be accessed directly through this page. I'll use this as the starting page today. So in terms of today's demos, I'll have 3 demos. The first demo is to show you how you can quickly and easily survey the available EM data for a broad category of interest, for example, human ribosomes. The second demo will be on locating specific EM density maps using advanced search features including wildcards, ranges, negation, and phonetic matching. And finally, I'll show you how to critically assess EMDB entries and examine the fit of a PDB model to an EM map. So I'll now go over to, I'll open up a browser and we'll start with the first demo. So please bear with me while we switch over to sharing a browser window. Okay. So to start off the first demo, I'm going to go to our EM resources page, which is pdbe.org/EMDB. And for this first demo, let's assume that you've been to a conference and you've heard a talk on human ribosomes and you're interested in finding out which entries are available in the EMDB relating to human ribosomes. Now, from this page, there are essentially three links to initiate a search. You can either use the search button here to open up a search form which you can fill out to initiate the search. You can press browse, which will allow you to browse the whole archive. Or if your search falls into one of these quick access categories, then you can click on one of these quick access buttons to initiate your search. Now, in all three cases, you have the possibility of filtering down your results to using search filters. So for this example, what I'm going to do is that I'll initiate the search by clicking on ribosome. And this takes you to a search results page. On top here, you have the number of entries that match the search criteria. So in this case, you have 251 ribosome entries. Below that, you have a panel of filters. And please note that this panel can be horizontally scrolled to access additional filters. And finally, below that, you have the search results. So we were interested in human ribosomes, so we can now use the filters to narrow down the search to just organism Homo sapiens. So if I click on Homo sapiens here, you see that the number shown here is updated. So you have 11 entries of the 251 original entries, which are human ribosomes. If you look at the filter items, you'll see that there are two numbers next to each filter item. The first number shows you the number of entries which have EM method single particle, which satisfy the current filters. And the second number here shows you how many entries with EM method single particle satisfy the original query without the filters applied. So in essence, if you want to narrow down your search, you choose filter items from different filter categories. So we could, for example, take, if I take single particle as the EM method, you see that the number here has gone down to 7. But you also have the possibility of broadening your the number of results shown, because if I click multiple items from the same filter category, you can see that this increases. So there are 9 items which can be either single particle or subtomogram averages of the human ribosomes. You may have noticed that while we have been clicking on the filters, this number has changed, but the search results have not changed. And in order to update your search results, you need to click on this button here. With the search results, you have the possibility of changing your sort order. So let's say that we want to sort them in terms of resolution. So we can easily find the highest resolution structure. So I take resolution as the sort order, and as you can see, the highest resolution human ribosome entry is 5592 by Ronald Beckman, which we'll use in the next demo as well. You can download your search results by clicking on download as text or download as XML. So if I click on this, and you have to contend sometimes with pop-up blockers, will allow pop-ups here, and then click on the button once again. You can see that you get a well-formed XML of the search results. You have the possibility of going to other external links. For example, if I click on Homo sapiens, it takes you to the taxonomy browser and shows you the Homo sapiens entry there. You have access to the publication. If you have several EM entries which are related by publication, the related EM entries are shown here. And if there are any fitted PDBe models, the fitted PDBe models are shown here. You have some summary information about the entry shown in the actual search results. If you want additional information, then you have to go to the entry summary page. And that you can do either by clicking on entry summary here or by clicking here. And this takes you to a summary page, but from this summary page you can access more detailed information. For example, if you need to download the map, you click on downloads here. And as you can see, you can access the map, you can access the XML header, as well as the fitted PDBe models. You may have noticed that there are two additional buttons here, the visual analysis of the map and the volume viewer. These are two means of analyzing and viewing the map in more detail. And this is what I'll take up in the third demo. But before that, I want to continue on the theme of the search. And let's say that so to continue on the example of listening to someone at the meeting. So let's assume that rather than wanting to find human ribosomes, you heard a talk by Ronald Beckman on ribosomes, and you want to search for all the ribosome entries which belong to Ronald Beckman. Now, one of the deficiencies of the filters here is that we do not have a filter category for authors. So although it's high on a list for implementing. So if you want to search for authors, you have to go to the search option, which presents you with a form where you can fill in different types of search criteria. Now the alt text box is the simplest box to use because it searches the sample name, the title, the authors, and so on. And if you want to find ribosomes by Beckman, we can, for example, type ribo wildcard asterisk and then Beckman wildcard asterisk. I need to have an asterisk here because Beckman is spelled with two N's. And if I now click on submit, you can see that there are 45 matching entries in the EMDB. You can see that these are related to Ronald Beckman. You can use wildcard asterisk wildcards at any position of the word, at the beginning, in the middle, at the end. But for convenience, we have made it so that you do not necessarily have to specify them at the end. So if you ignore putting wildcard asterisks, you still get the same results. Now, let's say that among the works of Ronald Beckman, you want to exclude in your search works by or entries by anger. In that case, you can simply negate anger in the alt text search. So if you type -anger, you can see that now there are only 32 entries, and if you were to look through all these entries, you would see that there were no entries belonging to anger. So I'm going to reset this form and just show you some of the other features. For example, with EMDB codes, you can specify ranges for the codes, and this requires a specialized syntax. So you have, let's say you want to find entries from 2000 to 2100. In this case, you have to specify 2 here in capital letters between 2000 and 2100. And as you can see, you have to specify braces or square brackets, and there's a slightly different meaning between them. So the square bracket means that you include 2000, whereas the brace here means that you exclude 2100. So this would do a search for everything between 2000 and 2099. So I click submit. We get these search results, and then if I sort by entry ID, can see that the search results start at 2000, and if I reverse the sort order, you can see that it ends at 2099. And please, I have checked that there is a EMDB 2100, so it's not that it's not showing it because it doesn't exist. So I'm going to reset the form and show you another feature of the search form. Let's say that you are interested in finding all entries in the EMDB which have fitted PDBe models. In that case, you simply type the wildcard asterisk in the fitted PDBe codes box. And this shows you that there are 424 matching entries. So going back to the example of listening to Ronald Beckman speaking at this meeting, what quite often happens when you hear people speaking at meetings and conferences is that you know the subject matter, but often with names you might have heard the name but you don't remember the exact spelling and so on. So we have implemented the authors field here so that rather than searching literally for authors' names, it matches based on sound, so it performs a phonetic search. And to launch the phonetics, so let's say that we mistype authors' names. For example, Beckman, we forget the K between C and M, and Ronald Beckman has the co-author Berninghausen, so we misspell his name as well, and click submit. And as you can see here that it's found the Ronald Beckman as well as the Berninghausen entries. So in addition to these features which I've shown you, there are a lot of more boxes present for other search criteria. For example, you can search based on resolution. You have the possibility to choose different types of software packages. With regards to microscopes, you can search based on different electron sources, acceleration voltages, and with microscopes, you have both the possibility of choosing different manufacturers as well as specific instrument types. So with that, I'm now going to go over to our third demo, and in order to do that, I'm going to return to the search results that we had, and the search result where we had the human ribosome, the high-resolution human ribosome by Ronald Beckman. So this is EMD 5592, and what I'm going to show you now is how you can use the visual analysis of the map and the volume viewer features. So let's say that you were interested in the human ribosome. You went and looked at this the journal article, which in fact is quite fascinating because the ATS ribosome, as the authors put it very nicely, can be regarded as essentially as having a 70S prokaryotic ribosome core with a layer. So if you look at lower eukaryotes, they can be regarded as having this prokaryotic core, but with the additional shell of protein RNA. And higher eukaryotes, for example, human or mammalian ribosomes, have yet another shell of RNA on top of this of the protein RNA shell. So this additional shell is partly quite rigid because of RNA-RNA interactions, but then you also have a lot of extension segments which are seen to be quite flexible. So let's Yeah, before we continue, I should just point out that these authors have been very diligent in depositing data. So not only have they deposited two EM entries relating to this structure, but they have also deposited all their fitted PDB structures. And if you took a look at their publication, they also had a very good supplementary materials section which allows you to actually relate what you read to these structures. So let's take a look at the visual analysis feature. Now the visual analysis feature allows you to do a basic sanity checking of the entry. And on the top we have just simple surface orthogonal surface projections of the map at the recommended contour level. Here we have a map density distribution. So on the y-axis we have the log of the number of voxels as a function of density. And here you can see often features which relate to different steps of processing that have taken place. For example, a spike at 0 often tells you that you've had masking done to this image. You have a discontinuity in the density here, which could be because of some sort of thresholding. You also have a oscillation here, which is quite unusual. We don't normally see this type of oscillation, but it could be due to the fact that there's been some sort of bit compression taking place. For example, the map has at some stage gone from a float representation to a byte representation and then back to a float representation. This red line here represents the contour level, which the recommended contour level. Here we have a plot of the volume versus the contour level. And as you can see, or as you would expect, if you were to reduce the contour level, then the volume enclosed by the surface is essentially the whole box. So you go here. And as you increase the contour level, the volume enclosed by the surface goes down to 0. This red line is the recommended contour level. And if you look at the intersection between the red line and the blue curve and read off the y value, which in this case is 1604, 1605 if you round it correctly, this is the volume of the map at the recommended contour level. In cases where the authors provide us with a recommended molecular weight, as they have done in this case, so it's 4.5 megadalton, we can use a conversion factor to convert this to an estimated volume. And in this case, we then show the estimated volume as this horizontal line. Now, in the ideal case, the horizontal line, the vertical line and the blue curve should all intersect in one point. But in this case, as you can see, based on the author-specified molecular weight is 5,000 nanometer cubed, whereas the one based on the surface is only about 1,600 nanometer cubed. And so there's a large discrepancy between these two. And one reason for this discrepancy may be the fact that you have all these, in the outer shell of the RNA, you have these extensions which are quite flexible and therefore are not well defined in the single particle EM reconstruction. In cases where authors provide us with the Fourier shell correlation curve, we show the Fourier shell correlation curve. In this case, they have provided us with the resolution which we show, as well as the method for measuring the resolution. So this was the analysis of the map only, but we also look at the fit between the map and the models. And in this case, there are 4 models that have been deposited. So first you have the model of the 40S ribosomal proteins. You then have the 60S ribosomal proteins. Then you have the 40S RNA as well as the eTRNA, and then finally you have just the 60S RNA. you look more closely at this, you can see that first you have a panel of 3 orthogonal projections where you see the overlap between the map and the model. Here you have a chart which shows you the atom inclusion by residue at the recommended contour level. And the way that this works is that for each residue, we look at the fraction of atoms which are included in the map volume, and then we put a color ramp on this. So green means that you have 100% of the atoms of the residue are within the map. If it's red, that means none of the atoms belonging to the residue are in the map. So ideally, you would want to have as much green as possible. Here you can see you've got quite a bit of red, but also a lot of yellow here. Here we have another type of representation of the same information. So here you got on the x-axis you got the contour level, and on the y-axis you have the fraction of model within the map. And we show two curves here. One, the green curve is for all atoms, so what you're seeing is the fraction of all atoms within the map. And then you've got a blue curve, which is the backbone. So in this case, in the case of a protein, it would be just the C alpha. So what you're seeing is the fraction of the C alpha atoms within the map. Now, one of the reasons why you have a lot of red and yellow here is something which quite often happens, is that the threshold is chosen usually so that it encapsulates mainly the backbone of the protein. And in that case, you have the side chains sticking out. If you look at this curve here, you can see that so the red vertical line here once again is the recommended contour level. Let's look at the all atoms curve. You can see that the all atoms curve is lower than the backbone curve, and the discrepancy is quite large. So this is a clear indication that the contour level has been set so that it includes the backbone atoms, but a lot of the side chain atoms are sticking out from the map density at the recommended contour level. If you look at the 60S ribosome, you see a similar situation, a lot of yellow. And again, in this case, in fact, you see a larger discrepancy between the all atoms and the backbone. Again, the backbone having a much higher atom inclusion than, the backbone having a much higher inclusion than the all atoms curve. Now, if you go to the RNA models, what you find is, one, you see that there's a lot of green here. And the reason for this is, one is that the RNA secondary structure they're usually much larger. But rather than having side chains sticking out with RNA secondary structure, you have the bases, you have base pairing, so you have the bases sticking into the density. So usually you have the backbone of the phosphoatoms running along the edges of the density, and you have the rest of the atoms facing into the density. And indeed, what you see here with the RNA models is a slightly different situation than what you see with the protein models, because in this case, there's a marginally higher atom inclusion for all atoms than there is for the backbone only. And this would be consistent with the fact that most atoms are, because of the base pairing, within the density, and it's actually the backbone which is running along the edges of the density. And you see a similar situation for the 60S RNA. You have a lot of green, and you see that the all atoms curve here is higher than the backbone only, which in the case of RNA is the phosphor atom curve. Now, this work was quite fascinating in the sense that they have used a number of different techniques to develop these models. So, for example, they used sequence to structure prediction, RNA prediction tools. They used X-ray structures from other species and modeled them in. Then they used, for example, molecular dynamics, flexible fitting to fit structures in. When you look at the paper itself, you have beautiful renderings of many of these models, and in many cases you even have cartoons overlaying what appears to be densities. But it's not very clear as to how much of this, of what is shown, is actually directly related to the model, to the map density, and how much is mainly model. And in fact, one particular example is there's a specific RNA secondary structure called the extension segment 27, which is purported to be in a very dynamic part of the ribosome. But there's a figure showing it as being a very nice, clean structure. So I was interested in finding out more about this structure. And luckily, with the excellent information provided by these authors, you can find that this structure is on the 60S RNA model, and it's between residues 2,800 and 3,600. So we can then use the atom inclusion by residue chart to locate that. So if you look here, here we are at about 2,900, and then if we go down, here we are at about 3,600. So it seems that the extension segment 27, although most of the RNA seems to be fitting very well into the density, this extension segment 27 seems to have a lot of atoms not well included in the map density at the recommended contour level. So I was interested in finding out more about this, and to do that, we can use the volume viewer. And I'll initiate the volume viewer by clicking on the volume viewer button here. And while the volume view is loading up, it's a Java application, so it takes a bit of a time. I would just like to point out that the volume viewer, unlike, for example, Chimera, does not require you to download any maps or download any software. And as a consequence, since it's running within the context of the browser, we have had to make some compromises in terms of how we represent the map and the model, because otherwise it would not be possible to show the map and model. And the compromise on the model front is that we show only the backbone-only structures, and on the map side, we have to downsample the map so that there are a maximum of 160 voxels in any dimension. So here you have the map and all the fitted models in all their glory. But since I'm interested in extension segment 27 on the 60S RNA model, I'm going to start by clicking off the other models. And I'm also going to click off the map so that it's easier for me to orient the 60S RNA model so that I can identify extension segment 27. And I'm doing this based on what I saw in the publication. And essentially this structure here appears to be similar to extension segment 27. So I'm also going to change the background here to black so it's a bit clearer. And just to make sure that this is indeed extension segment 27, I'm going to click on some of the atoms. And when I do that, you can see that it shows me the residue. So that was residue 3,289, which would be consistent with the range. And let me check another one, 3,200 and 2,900. So indeed, this seems to be the right segment. So let me then center on this segment, and you do that by pressing the letter C. And unfortunately, it zooms all the way up. So in order to de-zoom the view, you can press Shift, left mouse button, and then move the mouse in order to de-zoom it. And I would also like to point out that you have a list of all the mouse controls here if you forget them. So I'm just going to recenter on one of these atoms. And this rotated view matches what I saw in the publication. So what I'm now going to do is that I'm going to turn the map back on. And rather than having a surface view of the map, I'm going to switch over to a mesh representation of the map. Scale it a bit more. And then to remove some of the background, I'm going to reduce the depth of view. And that you can do by changing the slider here. But when it comes to small depths, it can be difficult to control by the slider. So you can use the minus and plus buttons on your keyboard. And then I'm going to zoom in a bit more. So if you look at this structure, you can see that it's not particularly well defined by, at least the map density is not well defined at this contour level. So what we can do then is to reduce the contour level to see if that would help. And you can see that as we reduce it, then you start getting a little bit more density. You can reduce it still further. And here you can see that although it's a bit noisy, you can see that there is density stretching along these along the modeled RNA. So although the secondary structure of the RNA is not clearly visible, you can still see why the authors may have decided to model it here. And this also alludes to the fact that this piece of RNA might be more flexible than some of the more rigid ones. So I'm now going to go back to the original threshold of about 0.7, zoom out a bit, and then take a look at some of the other modeled RNA. To do that, I'm going to increase the depth a little bit. And I'm clicking here and then pressing C once again to center it on this piece of RNA. And as I rotate it, you can see how well the density, how well the model fits into the density. You can see that it indeed spirals around as one would expect. And you can also start understanding the atom inclusion plots that we have seen, because you can see that the backbone is along the edges of the density, so it would not be uncommon that some parts of this may stick out of the density, but you can see that the bases would be sticking into the density. So I'm going to zoom out once again. And then, so we've looked at the RNA, the quality of the RNA modeling. So let's take a look at the quality of the protein modeling. And to do that, I'm going to switch on the protein 60S model. And I'm going to just orient myself again so that I can see. So here we have the extension segment 27. And I'm particularly interested in a piece of protein which is in close proximity of extension segment 27, which is in blue here. So to make it easier to manipulate the view, I'm going to switch off the RNA model, and I'm going to switch off the map as well. And I'm going to then zoom into the protein model and center on one of these alpha helices. and then redo the depth so that we can look at the alpha helix well isolated. Okay, and then I'm going to switch on the map again. So you can see that here we can see this, that the density or the contour level seems to be such that the densities follow the backbone quite well, but if you were to model in any of the side chains, you can well see that some of the side chains would pop out of the density. You can see some densities here which might be relating to side chains. I would like to point out here though that due to the downsampling that we do, these maps are usually reliable insofar as that you want to look at secondary structure. If you do want to look at side chains, you would have to download these maps and take a detailed look at them in, for example, Chimera. So if you look at these two, if you look at this helix here, you can see that at least the backbone is quite well modeled. And you can see that these atoms belong to the Z chain, for example, residue 116. You have a helix here which seems to be less well modeled, and we can take a look at, for example, here you've got residue 90. Now, you can relate these atoms back to your visual analysis graph. So we can, if we go back to the visual analysis, and if I then go to the 60S ribosomal proteins, and this was the Z chain, and if you try and find residue 90, so you can see that residue 90 here is has an atom inclusion of 0.42, but it's in general in a very red region, whereas if you look at residue 116, you can see that it's more in a green region. You have a higher atom inclusion. Now, you might be surprised by the fact that the atom inclusion for the 90 is not as bad as it appears when you look at it in the volume viewer. And here you need to keep in mind that one reason could be that although the backbone atom is out, the side chain might be sticking into the density. So here's once again a view of the secondary structure helices. We can now take a look at some of the beta sheet structures. So if you look at, for example, if I increase the depth here, so behind these alpha helices, you've got a beta sheet structure. So if we zoom into that, and then reduce the depth, so once again, I'm just trying to isolate them so it's easier to look at. And then if you turn the map back on, you can see that whereas we could see a relatively good definition of the helices, you can't really, as cylinders, when it comes to the beta sheet, you can't really see clear strand separation or any clear definition of the secondary structure. And I can change the depth a little bit to see if that helps, but as you can see, the resolution here is not sufficient to look at strand separation. And indeed, to be fair to the authors, they clearly state that the resolution is not sufficient to look at these types of features. And with that, I would like to finish my third demonstration and go back to the PowerPoint. So I hope I've been able to show you that we have a number of very useful tools both for searching, visualizing, as well as analyzing EM data, which are all web-based tools, so they don't really require you to download any data and or software. As we mentioned at the beginning, so all these EM resources can be accessed through our EM resources page, which is pdbe.org/emdb. If you want to get in touch with us and find out more about us, you can join us on Facebook as well as on Twitter. And I would also like to point out that we have a number of different very useful RSS feeds. For example, each week we have new EMDB entries, and if you subscribe to these RSS feeds, you would have access to the new entries as they came out. So in particular for the new EMDB entries, the RSS feed is given by this URL. And I would then like to finish by thanking our funders for providing the support for the work on the EMDB project. Thank you.